Welcome friends, I am Tanmoy. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we will discuss about aromatic electrophilic substitution, basic concept and mechanism. In my previous video, I have discussed about the basic difference between an alkene and an alkene. So I believe initially we all used to learn about alkenes, means a simple double bond. Alkene means a simple isolated double bond. This is called alkene. And benzene, you can see it's a cyclic triene. Cyclic triene. Is it visible? Yes. Cyclic triene we can say. So the thing is that benzene is cyclic conjugated a triene molecule. What is its difference? So before going to that, I believe you should have idea how benzene looks like. From this you can see benzene's formula is C6H6, means there are 6 carbon, 6 hydrogens, means 6 hydrogens are in this way. This I am not showing every one. So this you may think like that, 6 hydrogens. Fine. So what happens? That they undergo aromatic electrophilic substitution. Why? I have explained in the previous video, just I am giving a brief. That addition reduces entropy, and second, addition loses aromatic stabilization, means the resonance energy of benzene, which is around 36 kilocalorie per mole. So this is not a good process. Okay? Instead of that, if it undergoes substitution, aromaticity is not lost. So that is the thing. So today we will discuss mainly about the basic concept, role of electrophile E plus and corresponding counteranion, role of solvent, electron richness versus reactivity, mechanism, sigma complex of its name as Whelan complex, some isolated sigma complex, that is the proof of this concept, and finally some adapt of pi and electrophile adapt, means it will give you idea that okay, this is the selection criteria for reaction. Okay, so before going to details, I suggest you, I want to give you a brief about the bonding of benzene. It will be useful for you. So this is a benzene having every orbital as a p orbital, and hydrogens are at this position. Okay, same. So this is actually a sp2 hybridized orbital. This is sp2. This is sp2. And this bond is also sp2. What do I mean? This carbon forms 3 sp2 hybridized orbital, and one unhybridized p orbital is here with having a 1 electron. And as you can see that here every atom is having 1 electron. They combine together and form 3 double bond. But this 3 double bond is not localized, because whatever you see here, benzene has a resonance form, there is a canonical form, that is it will come here, it will come here, it will come here. So it should look like this. So it means the bonding between these and these and this, means this orbital is bonded to this and this both. So actually what they have done, they made a conjugated system. How it looks like? This orbital, as you can see, this using this line, they are bonded to each other with a particular symmetry. This below part, bottom part, bonded to each other with another particular symmetry. So what does it mean? It means that they are bonding. This bonding is actually, if you think properly, so it should look like, this, having a pi cloud on the above and on the below. Its symmetry is different. If it is plus, this is minus. Okay. And this should be represented easily using a forced diagram. So this thing is this left side diagram. This is known as forced diagram. Okay. So what is it? Actually, benzene has 6 electrons. This is actually a MO diagram of benzene. How these electrons are there? So benzene has 6 electrons and we have 6 orbitals. Okay. So these 3 are bonding. This is 1, 2, 2. These 3 bonding, and this 3, 3 and 4, they are anti-bonding. Okay, so what happens? 6 electron, they will come here. here. And what is this? This is called alpha. This is the energy of p orbital. Okay, so this indicates that all electrons in this. So if any reaction happens, any reaction means electrophilic. What is the word electrophilic means? That word electrophilic means electron loving. Philic word means loving, and electrophilic means electron loving. Okay, so something is electrophilic means electron loving. So if we say it's electron loving, then actually, okay, electrophilic means electron loving. This is electrophilic, means electron loving. I shall come then. Benzene is electron rich, so it will not like electron. Benzene is actually nucleophilic. Okay, benzene is nucleophilic, means nucleus loving, means it loves positive charge, means positive charge. Okay, so this is the energy of the p orbital. Fine. This is so expected that opposite loves each other, attracts each other because they are complementary to each other. That is the thing is happening is here. Means this has excess of electron, this is deficient of electron, so that react. And when nucleophilic means it has to give its electron, from where it gives electron? From this or this. It gives electron to the electrophile and react. So let's discuss a little bit about electrophiles. I shall make very soon I shall make a dedicated video on electrophile. We will have a complete idea about that, but let me give you a very brief about the electrophiles. As I said, electrophile means electron loving species. So what we think that what we can expect, that loving means it has to accept electron, means it has to accept electron, accept electrons. Okay, where it can accept electron, it can accept vacant orbital. It should have vacant orbital to accept electron. And generally for our organic chemistry thing, since we are dealing with carbon, nitrogen, this thing, generally p orbital, generally, but it may be different from case to case. P orbital. Okay, fine. So this indicates that they are Lewis acid. Since they can accept electron, they have vacant orbitals, so they are Lewis acid. Because Lewis acid means that they are capable to take electron from somewhere else. So what we concluded, that they are electron deficient Lewis acid. They could be positive charge or could be neutral. So another criteria, this is one criteria. Second criteria, they could be positively charged or they could be neutral. If neutral, they are deficient of electron, compared to actually they are electron deficient means less electron than corresponding stable electronic configuration. I have to explain this little bit. What I mean. For example, if you take boron, means B, let's say BF3. This is electron deficient. 6 electron, so it's Lewis acid. AlCl3 similar. If we take FeCl3, it is not related. Actually, this is not an octet. It needs 18 electron to be satisfied. So it depends that how many electron which one need. That's why I am saying less electron than corresponding stable electronic configuration. So it is not always true that if any such type of things are given to us, we will say they will be electron deficient if not octet filled. Because right now in case of organic chemistry, this octet rule is fine because we are dealing mainly with carbon. But when we will study about organometallic chemistry, then you will be able to learn that not only carbon, if we use metals, then another rule operates properly, that is 18 electron rules. Okay, fine. So this is the role of electrophile, and actually we have chosen here EX. Why? EX, the reason for choosing EX means EX will produce E plus and X minus, and another criteria of X, they must be stable enough. Stable enough that it allows free E plus, because if it is not stable in this anionic form, it will try to combine E plus, and if they combine, then reaction will not happen properly. So that is the reason. So fine. Now we have discussed about this iron 3, aluminium 3, etc., which is acting as a Lewis acid. Now very important factor comes, that when we have done the halogenation, for example, let's consider about the bromination little. So bromination of the alkene, what happens at that case? This is the alkene. If we treat with bromine, what happens? It reacts with bromine. How? This double bond donated its electron to the pi star of bromine, vacant orbital, this, and in this way a pi complex is formed. Okay, then what happened? It resulted in and for this thing I have uploaded a video, halogenation of alkene. Please go through if you want to have a greater understanding, and I believe if you go through it will be helpful for you. This is bromonium, and what it forms? It forms bridge bromonium and bromine minus. Fine. Secondly, it attacks, and in this way addition reaction goes on. But what happens in case of benzene? So if you do this thing in case of benzene, reactivity pattern is little different. Why? What do I mean? I mean that if you do this with benzene, so it will not react with bromine. If you take benzene and bromine, no reaction. No reaction. So this is the actual difference between the alkene and aromatic thing, means benzene. Some good explanation you will find in the previous video about the basic concept. Fine. So no reaction. But how to execute this reaction? You can add iron 3 plus or aluminium 3 plus or other Lewis acid. Even you can use metallic iron. Metallic iron. So when I am saying iron 3 plus, aluminium 3 plus, it's okay because we can understand that they need electron, that's why they are accepting electron. Fine. But when we are saying metallic iron, this is iron 0. How it's doing acting as a Lewis acid? Because it's electron deficient actually. Actually, it reacts with the bromine in the reaction medium or halogen. And keep it in mind, this concept is applicable for bromine or chlorine. For iodine and fluorine, different types of pathway followed, or they are prepared from corresponding bromo or chloro derivative. So what happened? Bromine, it prepares iron FeBr3 and Br minus. 3 Br minus. Okay. So this they do, and they in situ generate that Fe3. That's how this reaction occurs. Okay. Fine. Okay. Now we have discussed about this electrophilic, this non-nucleophilic nature of X, and so this fine. So we have discussed till now the basic concept, role of E and X. Let's discuss about the role of solvents. So generally, such type of reaction we use relatively inert solvent. Inert solvent. So what do I mean by inert? Actually, in this case, the definition of inert solvent is little difficult. Here, it doesn't mean that it is a hydrocarbon. No, it does not mean. It does not mean that it should be. It should be hydrocarbon. Generally we say that inert solvent means hydrocarbon because they don't react properly, but here the definition is little different. Inert means less electron rich. So what is the meaning here? This indicate less electron rich than benzene. When we are dealing with benzene, so our reagent should be more electron rich. Why? Because reagent is giving electron to this electrophile. So if the solvent is more electron rich, so instead of reagent, the solvent will react with electrophile. So there will be reaction, but not our target reaction. Okay, so that's why this. And for this case, what is our choice? In this case, we choose generally nitrobenzene. This is nitrobenzene. Generally, we write this as NO2. I have given the structure. Why? Because of resonance, it withdraw electron density from this nucleus. How? From here, here. So this is plus. What is the canonical form? So this is plus here. This is double bond. This is N. This is double bond here. O minus and O minus. This is plus. So similarly, other canonical forms are also possible. I am not right. So this indicates that because of the withdrawing nature of nitro, this is electron deficient. That's why we will prefer to use nitrogen. So I shall explain these in details when I shall discuss about the halogenation or nitration, those things you will learn properly. So solvent we have discussed, and this indicates that electron richness of the solvent should be lesser than the reagent. This we have learned from here. Okay. So now let's discuss about the pi and E electrophile adapt, because it is important. As we are saying that this such type of reaction happens, then what? So in the previous, at the beginning, we came to know that benzene, this is actually a pi cloud. Okay, this is actually a pi cloud. So electrophile can come and sit on the pi cloud. Fine. So this is this, and they can form a adact. Okay, so they can form adact. Who can form adact? For example, if you check, this is like halogen, they can form adact. Silver plus type Lewis acid, they can form adact, and actually they could be characterized. The interesting point is that another thing, not only silver, this is benzene is relatively electron rich, and means, okay, if we take picric acid, what is this picric acid is? This picric acid is trinitrophenol. This is OH, this is NO2, this is NO2, and this is NO2. This is called picric acid. So as previous time I have shown one nitro withdraws, here 3 nitro. But you can give me one counter argument that there are hydroxyl also. So it is electron donating. I agree. But actually the reality is that this 3 withdraws more compared to the donation of hydroxyl, and as a result this is electron deficient. This benzene nucleus is electron deficient. Okay. So if it is electron deficient, then what can happen? This is electron rich, so pi-pi type interaction, and in this way they form the adact. So this is the generally strategy that they will form adact. So 3 types possible. One is halogen, because halogen are energetically accessible orbital where the electron density could be taken. This silver, because it's plastic metal, d orbital, and this is picric acid, and they are called charge transfer complex. Okay, and they could be characterized properly. So after some time I shall give you real isolated example of this valent complex. So let's discuss now about the mechanism. So what happens? Initially this benzene reacts with this E plus. Okay, and by the way, E plus could be H plus, could be Br plus or Cl plus. You will be surprised why I am saying how this Br or Cl, generally we have observed the negative values. Even other metals like other organic ligands like this is, I guess you know, this is acylium cation. Okay, so such type of thing. So just I am not focusing on this. Our focus is on only this halogen right now. So what happens? This, if you take Br2 plus FeBr3 or FeCl3, whatever, Cl3 or Br3, whatever. What happens? That one bromide, when this, because this is the electron deficient, so this Br2 could be represented as Br, and this bond it attacks. So what it forms? It forms Br plus Fe Br4 minus. Is it isolable? No. Actually, to give you a proper understanding, I have written this. What happens? In case of simple double bond, if you give bromine, reaction happens. But if in case of aromatic, don't happen, because electrophile needed to be stronger. What do I mean? Electrophile simply means deficiency of electron or love electron deficiency. So deficiency need to be increased. Compared to this bromine, if you may think like that, this bromine, actually the thing may be, this is FeBr3. So now you agree that this bromine has a plus charge, this is a minus charge. So if it is plus charge, it will pull the electron density from this, and ultimately this bromine will be highly electron deficient. So the pi cloud electron will be attacked here and reaction will proceed. Okay, this is based on the physical evidence that if you put alkene and bromine, reaction doesn't happen. Alkene and bromine reaction happens. But if you provide benzene and bromine, reaction doesn't happen unless you put a Lewis acid catalyst. Okay, fine. So it forms a sigma complex or a Whelan complex. What do I mean? This means it will give and it will produce plus charge is here. This is one hydrogen previously at this center, and right now this is electrophile. This rest of thing, this is resonance stabilized, means it will come here. So the positive charge is here, double bond is here. This is H, this is E. Similarly, this position it will come. So I am not going to draw everything. So this is called sigma complex or Whelan complex. Sigma complex or Whelan complex. There may be some spelling mistake. I always suggest you, please verify with your books. So fine, this is, now we got this. What happens in the next step? In the next step, aromaticity is regained. How? See, we have given E, so there is some X minus. Actually, that is stabilized with this, means this is stabilized in this form, but it doesn't mean that it is completely, because it forms a charged thing. So at this situation, this react and abstract this. So what it produces? This is E, and this is the double bond, and XH. This X abstracted H. So you can now clearly see that whatever we have written here HX, we have actually this HX. Fine. Now question, why this step is happened? The basic, the reason, the driving force is to achieve aromaticity. And we know aromaticity is a very high and significant stabilization factor. So this is okay. So let's continue the discussion about the mechanism. Okay, this mechanistic thing could be represented by Hammond postulates. Hammond's postulates. How? So let's draw a reaction coordinate. This is the energy and this is the reaction coordinate, RC. Is it visible? Yes. So this is the RC. So what happened? Initially, this benzene, which was stable, so it undergo reaction. This is benzene. It undergo reaction to produce this intermediate. So this is the intermediate, means the sigma complex. Okay. So it looks this. This is the E, this is the A, this is the plus chain. Now this sigma complex is reacting, losing this proton to gain the aromaticity, means from there to this. So this, it should be little, it could be depending on the nature of E, the energy of this substituted could be little higher or could be little lesser compared to benzene. So just it doesn't matter. So this is the E. Now actually I should draw it little better way. I guess I have made little mistake. So its corresponding energy will be little more higher. Okay, this. So the energy of activation. So the energy of activation for this is EA for delta EA for losing of aromaticity. Okay, so this much amount of energy is wasted to get the intermediate, this cation. But here this ultimately after co-abstraction of proton, this converted into this aromatic. So this is the TS1 and this is the TS2. So this is lesser. So consequently, actually what happens? There are no evidence. The rate equation looks like rate constant into concentration of aromatic, let's consider as benzene, into the concentration of electrophile. Okay, and this is the RD step. So this first step, so this step, this is the RD step. This may be little slow, maybe little fast, but this is not RD step. Actually, this is very slow because of aromaticity losing. It's not a joke. I mean, it's a huge amount of stabilization is lost in this process. So that's why this is the RD step, but this is not. So this is the second step. So actually this is the RDS and second step, this is fast. Generally this is fast because aromatic stabilization is regained. So this is the overall thing. And now one thing is pending about some isolated sigma complex. Okay. So you can see there I have mentioned two examples where this sigma complex or valence complex could be isolated. Okay, but keep it in mind under low temperature condition. The first example will give you a real example. Actually, keep it in mind when such type of isolations are carried out, the reaction scheme is designed properly. See here. So this is mesitylene, 135 trimethoxy, 135 trimethyl benzene. Trimethyl benzene or mesitylene. Okay, so from this thing you can observe that only one position, these three are same, so only one position this electrophilic substitution possible. These three anywhere means one type of position. So this is BF3, as I told, this is a 6 electron fissile in my previously I have explained. This is a Lewis acid, and in presence of ETF this produces. But what is happening? This BF3 plus ETF. If you check, for example, this alkyl bromide, okay, you will find in next alkyl field capped alkylation. I will explain this thing. Actually, this is a field capped alkylation type. So, what happens? This fluoride is transferred to this boron, and another thing, what it produces? It produces BF4 minus. Formal charge is on the boron plus ET cation, ethyl plus. And this ET cation is actually the electrophile, ET plus, so it reacts and ultimately produces, already there is one hydrogen, so this is isolated. Okay, this, and after if you increase, means from 80 degree centigrade to isolated, actually reaction is carried out 80 degree centigrade, but this product is isolated at minus 15 degree centigrade. Okay, low temperature, fairly stable. So what happens upon heating? this undergo elimination of this proton. As I told that here aromaticity has lost, so this is a positive charge is distributed in this carbon, that's why I have given in this way. So next, when proton is, this is aromaticity is gained, ethyl benzene. And why this is? Because this BF4 is non-nucleophilic and non-basic. This is a very unique basic anion. This is a very unique property of BF4 minus. That's why it is chosen. This non-nucleophilic, non-basic. And what is the ultimate product along with this HBF4? Okay, so if that is the reason it could be directly isolated, but means actually directly observed, but indirectly this thing also could be seen. One of the example is using superacid. You know, I have already uploaded a video about the superacid. From there you will have a clear idea that how much extremely acidic they are. Actually they are extremely acidic. Super means super. Generally we saw very good means super, so this is extremely acidic. So they are capable to protonate anything. Means I should not say in that way as a chemist, but they are very efficient in protonating. So superacid can protonate this benzene to prepare this thing, because this is the simplest. Proton is the simplest electrophile. Why I am saying simplest electrophile? Why? Because has no electron. Only one proton is there. Means in this contain only one proton in the nucleus. No electron is there, so it's electron deficient. So this is, but this is could be done only using superacid under low temperature. Okay, so this is the uniqueness of superacid that it could be. And another advantageous thing is that when you can detect this thing using NO spectroscopy also. What do I mean? So if such thing happened, if this is formed, then this is cationic. So you will have more de-shielded 13C positions. Actually for HS students +2, please skip this part because 13C NMR you don't know, you will not be able to understand. So please skip this part. This example you will understand. So 13C, this higher position, higher 13C value of a particular carbon will be more de-shielded left side. Okay, so higher value. So that's why that is the another proof that this this protonation or cationic species formation is achieved. Okay, fine. So another example. This example is not the directly proof. Indirectly it supports, means logically if we think that during this reaction we are getting this product, how this is happening, then you will be understand that this is forming. So this is actually a methyl substituted and oxygen, means phenolic type. Phenolic, this is a phenolic ether, you can say this, and this is a clever design. I always say bromination using bromine if carried out in presence of. So what happened that it undergo bromination? So three types of position possible: this position, and this position. Now see, they are a big group. This methyl, this. So it is expected that probability at this position is be less due to the steric effect. So consequence ortho is blocked, so para. So if bromination happened, means Br plus. Okay, so it reacts. So you can think that it pushes its electron. Okay, let's not complicate this. First, let's draw it. This is the Br. This is the methyl. This is. So this is O. This is C double bond O, and this is OH. Fine, these are two methyl. This, I believe this is a design substrate. I'll explain why this is a design substrate. So this, And now see, the positive charge is here. So next time what will happen? This will come and positive charge will go there. So in this way positive charge will be stabilized. So let's draw it again. This is methyl, this is bromo, this is O, C, sorry, this is methyl. This is methyl, OH. Okay, now positive charge is here. This is stabilized. This can further resonate or it can stabilize with the lone pair of oxygen. Fine. But see what happens. Next, this attacks here. So when it attacks, so it produces. This is Br methyl. This 2 methyl. This is the oxygen and this is the C double bond. This is 1 methyl, this is 1 methyl. Fine, now see, we know the electron density of this oxygen is more compared to this, so this is attack, and after that elimination of one proton. So proton elimination is the second step of aromatic substitution, so proton eliminated but from different side. And that is the beauty of this design. First beauty, that para position instead of hydrogen there is 1 methyl, so it could not be eliminated easily. So para blocked. You can say blocked para position. Blocked. Find this. So now it will come here and see the design that oxygen this has that 5-member ring forms, and second interesting point which I found is the presence of methyl. Presence of this methyl helps to ring formation. I will explain this thing in later some videos. This methyl affects the ring formation, that's why this attack and forms the ring. In this way this reaction, and this proves clearly that positive charge comes here, otherwise this will not attack. So this is an indirect proof, that the indirect proof for the isolation means indirectly by formation of some another complex, this sigma complex is isolated. So this is the end of this discussion. So what we have learned, I know it's a big lecture. So what we have learned today? We have learned the basic concept of aromatic electrophilic substitution, role of electrophile, Lewis acid, product, why not addition, substitution, mechanism, solvents, and finally the isolation of intermediates. So this is the end of this discussion. Thank you everyone for listening. If this video is useful for you, please share this to many friends of you, such that many people could be benefited from my effort. So in next video, I shall try to explain that electrophiles. Okay, this is a very important thing which I should have been explained earlier, but I understood later that I shall upload. So thank you everyone. Stay happy, stay blessed. See you in my next video.